So let's do y equals 1/2 secant 1/3 x. To find the domain and range, I would graph it. I mean, you don't have to, but it's going to make your life easier if you go to graph first, I think. But there are other ways to do it. But let's go ahead and graph it and do it that way first, and then maybe we can discuss the other ways to make it do it. So how would you graph 1/2 secant of 1/3 x? Start with cosine. Right? So let's first graph 1/2 cos 1/3 x. And how's that work? Label your A, B, and C, right? A is 1/2, B is 1/3, and C is 0. So that means your period is equal to what? You do 2 pi over B, which is 6 pi. Well, I've got your amplitude. Your amplitude is equal to 1/2. And then your quarter period, cut 6 pi into quarters. 6 pi over 4, 3 pi over 2. You reduce. And your phase shifts, well, C is 0, so you have no phase shift. Then you can get a graph of cosine, which looks like, since there's no phase shift, I'm going to start on the y-axis, and then to get my next x values, I have to go 3 pi over 2 to the right. So I'll go 3 pi over 2, and then if I go another 3 pi over 2, I'll be at 6 pi over 2, and then 9 pi over 2, and then 12 pi over 2. Okay, fair enough. So then, since the amplitude is 1/2, this will be 1/2, 1/2. And I'll graph cosine starts from a max, a min, or 0. Max, 0, min, 0, max. And I'll go ahead and put it dotted, right, since we're going to do secant on top of it. Now, it's very nice to start at an asymptote when you start graphing secant, so I'm going to go ahead and go back 1/4 period. What would it be if I went back 1/4 period? Negative 3 pi over 2. So then these are my asymptotes. Here, here. And then let's talk about secant. To get secant from cosine, you flip it up. Right? One stay the same, but a max turns into a min. So secant will be right here. Click going upward. So then, that's the black graph is the secant graph, but what you actually asked me for were domain and range. So let's start with range, actually, because it's easier. What's the range here? So the range for the secant graph is everything above this 1/2 line and everything below this negative 1/2 line. So if you're using y's and x's, you could say that the range is y greater than or equal to 1/2 or y less than or equal to negative 1/2. These two restrictions work for the range. If you're doing interval notation, you would do 1/2 to infinity union negative 1/2 to infinity. This means the same thing. Everything bigger than 1/2, everything negative infinity. Everything less than negative 1/2. So I'm just looking at the picture, and I see right here is my lowest y value, and right here is my, right here. This is my lowest, and this one is my highest. So I'm going everything above that, everything below that.
I have a question.
Yes, miss.
With know how you put -1/2, comma, -1/infinity? Would you put -infinity and then -1/2? Would that still be correct?
Oh yeah, actually this is garbage, right? This is garbage. Good call. And you said it very politely too. This should be -infinity to -1/2. You have to put the smaller one first. You have to. So what I wrote was wrong.
I didn't know that.
Oh, so we know that.
I wasn't trying to be polite. I'm just.
No, that's good. That's good that you told me. It's good that you spoke up. So that's how you have to write y less than or equal to -infinity. The smaller number always comes first in your implementation. Domain. Domain's a tricky one. Right? It's clear you stay above 1/2 and you stay below -1/2. But it's maybe a little bit more difficult to figure out where you're undefined here. So what x values do you have problems at here? So let me list my restrictions. So what happens is, at -3π/2, 3π/2, 9π/2, you have problems, right? So x cannot equal -3π/2, 3π/2, 9π/2. But that's not all the problems, right? Because I've only graphed one period. So how, what's the pattern, or what would the next asymptote be at? 15π/2, right? And what would the next one be at? And how are you getting that? You're adding 2 quarter periods every time you get an asymptote. Right? 1 2-quarter periods asymptote, 1 2-quarter periods asymptote. And if I were to go back this way, what would be my next asymptote on the left? So x cannot equal these. So these are your restrictions. And you know what? I'm not going to be super hardcore about this. If you list some of these and then put ... I will accept that. Which means it goes on in that pattern forever. If you don't use ... if you don't use an ellipsis, then you're going to have to use some sort of n or k to express general integer.
That's what I had trouble with in homework.
Yeah, so
How to list it.
yeah, well, I mean, to list all possible asymptotes, to list all possible restrictions, I would start from one of these, pick any asymptote, pick any one of them, right? This one. Pick any asymptote. And then add to it, how much do you have to add to it to get to the next asymptote? 2 quarter periods, which is 6π/2. Right? But you can add any multiple of that. Right? If you add 2 times 6π/2, that will give you the second asymptote. If you add 3 times 6π/2, that will give you the next asymptote. So this is really the crucial, this 2 quarter periods here, times any integer will give you all the formula for all the asymptotes in this particular. We're going to talk a lot more about this guy right here, this n, today. So for now, I would say you can just list me a few of them, all right? But after today, hopefully that n, that general integer n, will make a little bit more sense. Let me finish up. Let me finish up 7.1.7.2, which is inverse trig function. We're a little bit behind. We left off talking about things like sine of sine inverse, right, of, I don't know, 0.65 or something. Or maybe cosine inverse of cosine of 3 5 pi over 4 cosine inverse of cosine. Give you one more to think about here. 18 pi over 17. So we started talking about what happens if you mix inverse functions with their original function. Do you remember anything about how this worked at all? They cancel, right? That's the hope. You hope and you pray that they cancel each other out. But it only works if you are within a certain range. So you have to analyze what your input is. So for example, because I'm inputting to sine inverse, does sine inverse eat angles or ratios? Ratios, right? So sine inverse takes in a ratio. This is a ratio. What do the ratios have to be between for sine? Negative 1 and 1. So as long as this is between negative 1 and 1, since I identified it as a ratio, this will cancel each other out. And it is, so these cancel. Right, that's when everything is rosy. Right? When everything works perfectly, that's what happens. Okay, now when everything doesn't work perfectly, you have to think a little more. In this particular example down here, again, you have to identify, at least one easy way to think about this is to identify whether 5 pi over 4 is an angle or a ratio. Which one is it? An angle, and how do you know? It's got pi. No, true, wrong. Because it's in cosine, not cosine inverse. Right? Cosine takes an angle. So this guy tells you that this is an angle. So then you think back to how we restricted our domain. You know, what kind of angles did we say were allowed for cosine inverse? 0 pi. So remember, I probably drew you a little schematic. I had it in a circle. That's like a circle. And I said, for sine inverse, you have to be between negative pi over 2 and pi over 2. All your sine inverse answers will fall in this area. Actually, that's sine inverse and tangent inverse. Which is easy to remember because sine is the y value, so you know your y-axis gives you your range for sine inverse. For cosine inverse, it was your x-axis. So for cosine inverse, you have to be between this guy, which is 0, and this guy, which is pi. Well, it's not. 5 pi over 4 is not between 0 and pi, right? Because it's 1 pi over 4 too big. So how do you think I can break this down here? Do you actually know what cosine of 5 pi over 4 is? Yeah. What is it? Yeah, I should know what it is, but now that you call me on it. Some kind of root 2 over 2, right? Every pi over 4 is root 2 over 2 for sine and cosine. So we're actually over here now. Oh, no, that's 3 pi over 4. Here's 5 pi over 4. Root 2 over 2. So the question is positive or negative x value? Negative. Okay. So at 5 pi over 4, cosine is negative root 2 over 2. So I'm going to replace this whole quantity here with negative root 2 over 2. But I haven't done this yet, so I have to go back, and I have to write cos inverse. So I do this piece by piece, start from the inside. Cosine of 5 pi over 4 is negative root 2 over 2. But then apply cos inverse. What's cos inverse of negative root 2 over 2? Cos inverse is an angle, right? So this is asking, which angle do I take cosine of to get negative root 2 over 2? You might think 5 pi over 4, right? Because here's negative root 2 over 2, here's 5 pi over 4. but that's crossed the boundary. So I have to find an answer that hasn't crossed this boundary. So I'm going to push it back up into one of these quadrants. 3 pi over 4, right? Because over here you're positive. This one doesn't work. But over here you have a negative root 2 over 2, positive root 2 over 2. So here's another place where cosine, where the ratio is negative root 2 over 2 for cosine. Which means cosine inverse of negative root 2 over 2 is 3 pi over 4. Because this angle is 3 pi over 4. So if you look at your unit circle, just to kind of put this all together, there are only so many places where cosine is root 2 over 2. Right, on the unit circle, these are the angles where you're going to have some sort of root 2 over 2. And depending on the quadrant, you get different signs. This is my boundary for cosine, for cos inverse, I should say. I have to be in here. So what I put in originally was 5 pi over 4, but that was outside of my boundary. So when I apply cos and then try to do cos inverse, the cos inverse is going to push me back into its boundary. So cosine of 5 pi over 4 gives me the root 2 over 2, negative down here. This part gives me this. But then cos inverse pushes me over here in a second, where it's defined. So the other one I gave you, cos inverse of cos of 18 pi over 17. This is the same idea, but I didn't give you an angle that you know the cosine of. Right? I gave you some random angle. Let me put one more set of parentheses. So, here's my diagram. 18 pi over 17, what quadrant does that land in? 5th quadrant. No. So it lands in 3rd quadrant, right? It's a little bit over pi. Right, pi is right here. 18 pi over 17 is a little bit more. So 18 pi over 17 lands just past pi. I don't know what the cosine value is here. It's some negative x value. But I know if I do the cosine value, I will get out this negative x. And if I do cos inverse after that, it's going to push me back up to the 2nd quadrant. This guy here. So you just have to figure out what this angle is in the 2nd quadrant that gives you the same cos value. 16 pi over 17. How'd you know that? Yeah, because there's one, we went one more here, right? We went an extra 1 pi over 17. So to get into the 2nd quadrant, we'd have to go back 1 pi over 4. So my overall answer to this is 16 pi over 17. I get pushed back into the 2nd quadrant by the cos inverse. Okay.
I have a question.
Mm-hmm.
For sine,
Yeah.
you know how you put -1
Yeah.
ratio in between
Yeah.
to 1? Well, I thought with first sign, it had to be between pi over 2 and negative pi over 2.
Okay, so that comes down to whether we're talking about sine of sine inverse of something or sine inverse of sine of something.
So if it was the other way around,
Right.
then
Right. So in this case, because you're going into the inverse first, the inverse needs ratios. So this guy will be a ratio. It's going to have to be between -1. But if you're going into sine first, this guy's an angle. And the angles for sine inverse for this guy, when you get to him, have to end up being between negative pi over 2.
So would that be what if cosine was switched? Would it still
Yes.
be -1 and 1?
Yes.
Okay.
Yes, so it's all about the order. You look at whatever you're feeding into first tells you what this should be, whether it's a ratio or angle.
Okay.
Okay. So when you mix, right? So we kind of talked about how to handle an inverse function with the original function if they're the same, but I kind of want to go over how to handle what happens when they're mixed.